Welcome to Strength of Material lectures by Civil Thinking, and this is our another class on torsion in shafts. Now before I move on, I suggest you to please watch the video lectures on torsion in shafts one by one in sequence as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now coming to today's class. Now in this class we are going to see, we will derive the equation of torsion. Okay, torsion equation for shafts. Okay, so before going into derivation, okay, so this is the preview of our equation. Okay, this is a very famous equation for the torsion in shafts. Okay, and I advise you to just remember it. Okay, understand it and remember it. Okay, because you are going to use this a lot in solving problems. Okay, so to derive this, let us first derive this much half, and then we are going to derive this much. Okay, so let's begin. Now when you have a shaft, okay, let us consider a shaft. Okay, let us say it is fixed here. Okay, it is fixed here and it is free here. Okay, now what you did, you applied a tangential force F. Okay, as I have told you in my previous class, when you apply a tangential force F, there will be torsion, right? There will be twisting in this shaft. Okay, so let me show you a line and I will illustrate the torsion with the help of this line. Okay, let us draw a line. This line is on the surface of this shaft. Okay, it is on the surface of the shaft, and when the force is applied, there will happen torsion, right? So after torsion, right, so what is going to happen after torsion? Because this is a fixed end, this point will not rotate. Okay, but because of this force, it will it will twist and this point will displace to some else point. Okay, I will show it here. So if I draw the same diagram again, now what is going to happen after torsion? It was the line, this was the initial position of the line, but because of the torsion, it is going to be somehow like this. Okay, now you will see this angle here. Okay, let us say this angle is phi. Okay, and you will also see, initially you will see no angle in the cross section. Okay, but when it will reach at this point, this line, right, so there will be some angle here. Okay, so initially the line was like this, but this line has reached to this position, right? So there is also an angle theta here. Okay, so by the way, theta is called as angle of twist. Okay, this is called as angle of twist. Okay, now this phi is along the length. Okay, so let us say the length is L, the length of the shaft is L. Okay, so we will divide this into two parts. Okay, first of all, you are going to see a triangular like thing. Okay, now this one is curved. If you assume it to be a straight line, okay, so in that case this is going to be a triangle on the surface of the shaft, and here also you will see this triangle or a sector, right, or a sector of a circle. So we will draw these two things separately so that we can understand better. Okay, so I will divide this, I will draw these two triangles, or whatever you call it, sector. I will draw them into two parts. Okay, first part is this, right, this is the angle phi here, right, this is the angle phi. Okay, let us say this point was O, this was A, this was, and it has reached to A dash. Okay, so after twisting, A has reached to A dash. Okay, although this is it is a curve, it is not a straight line, but to derive our this torsion equation, it is safe, okay, to assume it like a straight. Okay, but in reality it is something like this. Okay, but we can assume it to be a straight line. Okay, so this is a straight line. Okay, now we will also draw this sector, but again, since we have assumed this to be a straight line, it will act like a triangle, right? So it is here, right? This is angle theta, and if it has a radius of r, okay, so this is going to be r, okay, this is also going to be radius r, okay, and this is a dash, and here we have this is a, it is a dash, and this is point o, okay. Now let us apply, this here, tan phi, okay. Now tan phi is, perpendicular, which is a dash, right? Perpendicular divided by base divided by OA. Now how much is OA? OA, it is equal to length, right? Length of this shaft, okay. So I can write this as a dash divided by L, okay. Similarly, we will apply tan theta here. Tan theta is going to be this perpendicular divided by base, okay. So it is going to be a dash divided by the, the base is r, okay. Now from here we will find a dash, and from here we will find a dash again, okay. So from here a dash is going to be L tan phi, and from here a dash, it is going to be what? R tangent of theta, right? So since they are both equal to a dash, right, this is equal to a dash and this is equal to a dash, so they are equal, okay. So from here I can write, so from these two, right, what I can write L tan phi is r tan theta, right. Now if we assume this angle is small, okay, and this theta is small, okay, it means there is, small distortion. So when theta and phi are small, okay, then tan theta can be approximated as theta, and this tan phi or tangent of phi, it can be approximated to be equal to phi, okay. So we can, rewrite this equation to be L phi is equal to r theta, okay. So we got this equation, and this is a very, important equation. It will help us, okay. So this is, from here we can find the angle phi because we will need it, okay. So L phi is r theta, okay. It means this phi is r theta divided by L, okay. So now what we got, we basically got a relation between this phi and this theta, okay. We got the relation between this phi and this theta, okay. So phi is what? Phi is the, the surface angle, right, and this theta is what? Theta is the cross section angle, okay. So we didn't have a relation between phi and theta, but now we have, and it is phi is equal to what? Phi is equal to r theta divided by L, okay. Now let us apply the, the relation of, definition of, let us see the definition of shear modulus. Okay, we denote it with C, and some books also denote it with G, okay. So when you see C or a G, it is one and the same thing. Basically, what is C? C is what? It is shear stress divided by shear strain, okay. Now what is shear strain here? Now this is our shear strain, okay. This, the tangent of this, the tangential function of phi is the shear strain here, right, because we have applied this F, okay. This F is, kind of tangent to it, and it has caused the distortion, okay. So the distortion is because of this force F, okay, because it will twist, there will be, it F acts like a shear force here, okay. So this is our what, the tangent of this is going to be what, it is going to be shear strain. Okay, so let us denote the shear stress with tau, okay, divided by shear strain is what, tan phi. Okay, so I have told you that phi is a very small angle and we can approximate tan phi to be equal to phi. Okay, so it is equal to tau divided by phi. Okay, now C is tau divided by phi, but what is the value of phi? Phi is r theta by L. Okay, r theta divided by L. Okay, so when we rearrange this, we will get, if we get tau L divided by r theta. Okay, so the value of C is this. Now we can again rearrange this, we will get C theta divided by L is equal to tau divided by r. Okay, so basically what I did, let me simplify it. I keep the tau divided by r separate, okay, and then L divided by theta separate, okay, and all of it is equal to C. Okay, all of it is equal to C, right, as you can see. So from here I can write, so if I throw this theta to the right, to this right, okay, so it is going to be C theta, L is going to be in the denominator, C theta by L is equal to tau by r. Okay, now you can see this equation, C theta by L is equal to tau by r. Okay, so it means we have successfully derived this part of the torsion equation. Okay, so now our job is to derive this much. Okay, so basically T is the torque and J is the what, polar moment of inertia. Okay, so we will find the relation between torque and polar moment of inertia, okay, and see if we get this C theta by L again. Okay, so if I write here a relation between torque is denoted with capital T, right, and polar moment of inertia, okay, we denote it with J. Okay, now by the way, I have already made a video lecture on polar moment of inertia of a shaft. Okay, and polar moment of inertia of a shaft, solid shaft, is given by pi r4 divided by 2. Okay, now I will provide the link to in the description about this, where did it came from. Okay, so you can watch it from there. So let us see this relation. Okay, relation between torque and T and J. Okay, now for this we have to consider this, we have to consider the cross section. Okay, now let us consider a strip inside. Okay, now what I did in this cross section, okay, I considered a strip, okay, inside. Okay, and we will analyze this for what, we will analyze this for the torque. Okay, and see if we get a relation between torque and polar moment of inertia for this strip, and then we will integrate it and we will get the T is the total torque, right, and we will integrate it and we will get the torque of the entire cross section. Okay, so that's what I did. Now if here the total radius is r, okay, the total radius is r, so let us say this is dr. Okay, not r, I mean capital R, because the total radius is r, right, so the total radius is r. Okay, so let me show you here. So here the total radius is r. Okay, let us say, because this strip does not it is not at the circumference. Okay, it is in between. Okay, so let us consider a small radius, small r. Okay, so r is less than r. Okay, So we have considered a strip, okay, and the thickness of this strip, okay, it is going to be dr, okay, it is going to be dr, okay. So what we are going to do, we are going to basically find this relation at this, okay. So let me draw this again here, this strip. I am going to draw only this much, okay, this strip, okay. So I draw this strip again, okay. The radius is small r and its thickness is what? It is thickness is dr, okay. So I can write here, let us say the force acting, because the total force acting here is F, right? Tangential force is acting F here, okay, as you can see here. The total force acting here is F, okay, F, but the same force won't be what? On the, below it, okay, because the force keeps on decreasing as we go to the origin, okay. So let us say on this strip the force is df, okay. So we have this df force, okay. So we can write df to be what? Df is going to be, we know force is what? Stress multiplied by area, right? This is the basic definition of a force, okay. Now force, what kind of stress do we have? We have this shear stress, okay. So let me grab it here. We have this shear stress here, okay, right. So from here we can get shear stress tau is equal to c theta divided by L times R, okay. So we will put this into this, but area, what about area? Now its area is going to be, what is the area of this? Area of this is total length, right? Length is 2 pi r, okay, times thickness, thickness is dr, okay. So its area is 2 pi r dr, right? Length multiplied by the width, okay. So I can write here df is equal to c theta by L times r times 2 pi r d r, okay. Or if I simplify this, c theta by L, now this is r and r is r square, so it is going to be 2 pi r square d r, okay. Now we found the df. Now remember, how do we find the torque? In my previous class I have told you what is the relation between torque. Torque is what? Force multiplied by lever arm, okay. So but for this inside the strip, because it is a small strip, so I can write dt is df, I mean yes, df times r, okay. This df, right, and the distance is r, okay. So the torque is going to be df times r. So I can write here, but we have this relation for df, it is c theta divided by L 2 pi r square d r, okay. Now what is this? This is tau. Let me show you one thing again here, because here the actual radius, the full radius is r, okay, capital R, okay, and not the small r, okay. Let me show you here, this here, yes, this is not r, right, this is total is capital R, right. So I have to write capital R here because it is very important. I will tell you why. So here we have, this is R, okay, capital R, okay. So here we get R again, okay. So this is R, this is R, and this is R, okay. Now from here what do I get? Tau to be we got tau is c theta divided by L times R, right? From this we got this relation, right? Now it is important to note this shear stress tau is what it is when we have the full radius R, okay, and tau is directly proportional to R. It means shear stress is going to be maximum at full radius, and the full radius is at the circumference, okay. So this tau that we are talking, it is basically tau max, okay, because when we have this full radius we are going to have the maximum torque, okay. And it, what does it mean? It also means tau at any radius small r, okay, less than r, is going to be c theta by L times small r, okay. Now you can see here this tau is directly proportional to r, okay. It means shear stress is more at what? Is more at when there is, you know, full radius, that is at the circumference, and when r is 0, which is at the center of the circle, the torque is, the radius is 0, it means shear stress is 0, okay. So if you draw a relation, I mean a diagram, okay, so it is going to be something like this, okay. So here you have tau max, okay, and here we have 0, okay. So this is going to be a linear relation between what? Between the shear stress and the radius, okay. So it was very important, okay. Now since here we are talking about the small radius r, so we are going to use the small r here, okay. So everything is good now. Now we have found the, you know, shear stress is c theta by L 2 pi r square dr, okay, 2 pi r square dr multiplied by this r, right, r, okay, or it is going to be r square and r is r cube, so it is going to be r cube, okay. Now this is what? This is the torque for this small strip, okay. Now if we want to get the torque for the, you know, entire, you know, this cross section, we have to integrate this equation, because it is in, you know, this equation is in terms of the function of this small r radius, okay. So we have to integrate it to the radius, and radius begins from the center. At center the radius is 0, and at the circumference the radius is r, okay. So we have to integrate it, okay, at this from 0 to t, okay, from 0 to capital R, right. It is going to be capital R, right. So let us integrate. Now c is constant, theta is constant, divided by L is also constant, okay, and 2 pi is constant. It is going to be integration of r cube dr, okay, and from here integration of dt from 0 to t, it is going to be total torque t, okay. So it is going to be c theta divided by L 2 pi. Now integration of r cube is what? Integration of x raised power n is x raised power n plus 1 divided by n plus 1, okay. But since it is a definite integral, right, definite integral means we have the limits and there will be no constant of integration for this, okay, because when we have limits there is no constant of integration, okay. So it is going to be 2 pi. So r cube plus 1, 3 plus 1 is 4 divided by 3 plus 1 is 4, okay. So it is r4 divided by 4. The lower limit is 0 and the upper limit is capital R, okay. So it is going to be c theta by L 2 pi. Now this r4, now here we will put the upper limit. It is going to be capital R4 divided by 4 minus lower limit is 0, so it all of it is going to be 0, so it is going to be R4 divided by 4, okay. Now if you remember something when you look at this, let me show you. We can write this as c theta by L. Now this 2 1s and 2 2, right, it is going to be pi r4 divided by 2. But what is this pi r4 divided by 2? Now if you remember from my previous class, I have told you, I mean from the classes of, you know, polar moment of inertia, okay, you will remember polar moment of inertia. of a shaft is pi r4 divided by 2. So pi r4 divided by 2, we will write j here. Okay, so it means T is c theta by L times j. Okay, and when we rearrange it, we get T by j is c theta by L. Okay, now this is our second equation. Okay, this was our first equation, right? This was our first equation, or this, even this. Okay, it doesn't matter. So what we got this T by j is c theta by L, and if you look here, T by j is c theta by L. Okay, since tau by r is c theta by L, and we also get T by j equal to c theta by L, it means all of them are equal. Okay, so this is our equation first. Okay, so this is our equation first, right? And this is our equation second, right? So we can write from first and second, what we get c theta by L is tau by r is T by j. Okay, so this is our final torsion equation. Okay, and I always advise you to just remember it. Okay, because this will be used to solve a lot of problems. Okay, and I think that's it. If you have any doubt, you can comment. Okay, and see you in the next class. Thank you.